In this lecture video, we're going to be looking at estimation in the context of the randomized complete block design. Now let's first look at the logical relationships among the constructs that we'll be looking at, and then we'll look at the conceptual development that will follow in learning how to estimate these constructs. So the logical relationships are as follows. The most general type of construct that we'll be looking at will be linear combinations of one or more treatment means. Now, as a special case of that would be individual treatment means. Another special case would be contrasts of two or more treatment means. And then a special case of a contrast of two or more treatment means would be differences between two treatment means. Now, we're not going to start here at the very top and work our way down. What we're going to do is actually start at the bottom on the left side. And so the first thing we'll look at will be point estimation of individual treatment means. That's a very natural place to start. And really, we have to know how to estimate the individual treatment means before we can do anything else. After that, we'll look at point and confidence interval estimation of differences between treatment means. We'll then look at point and confidence interval estimation of contrasts of two or more treatment means. Then we'll look at point and confidence interval estimation of linear combinations of one or more treatment means. And then finally, we'll work our way back to the individual treatment means, and we'll see how to construct confidence interval estimates for those individual treatment means. And so from the standpoint of the conceptual development, we'll look at point estimates of individual treatment means first. Then we'll look at point and confidence interval estimation of differences between two treatment means. We'll then move up in our diagram and look at point and confidence interval estimates of contrasts of two or more treatment means. We then move to the very top and look at how to construct point and confidence interval estimators of linear combinations of one or more treatment means. And then once we see how to construct confidence intervals for linear combinations of one or more treatment means, then we'll be equipped to be able to come back down and construct confidence intervals for the individual treatment means. So let's first look at point estimation of individual treatment means. And we're going to be looking at the situation where the treatment effects are fixed effects. So recall that the means model representation of the randomized complete block design is given by this model here, y sub ij equal to beta sub I, which is the effect of the ith block, plus mu sub j, which is the effect of the jth treatment. Again, mu sub j, the treatment effect is a fixed effect, and so mu sub j would be the mean of the jth treatment. And then plus the random error term, epsilon sub ij. Again, the first subscript I corresponds to the block, I going from 1 to r is the number of blocks. The second subscript, j, represents the treatment, and there are t treatments, and so j is going from 1 to t. So y sub ij is the response measured on the experimental unit that is receiving treatment j in block I. And beta sub I, again, is the effect, the random effect, of the ith block on the response. Mu sub j is the mean treatment response under treatment j. Again, treatments in this context are fixed. And then epsilon sub ij is the random error associated with the experimental unit receiving treatment j in block I. Now, the goal here is point estimation of the treatment means. In other words, estimation of the mu sub j's. And so an unbiased estimator of mu sub j, which again is the mean treatment response under treatment j, is provided by the mean of the sample receiving treatment j. All right, so y bar sub dot j. All right, so that is the notation we're using for the mean of the responses that are receiving treatment J. So this is an average across all of the blocks here. We can see that we take every observation, every experimental unit in each of the blocks that has received treatment J. We measure the response on those experimental units, and then we're averaging those responses. And because this is an unbiased estimator of mu sub j, we will denote it by mu hat sub j. All right, so this is our point estimate for mu sub j. Now, in order to go any further, for example, to construct confidence intervals for mu sub j, or perhaps to test hypotheses about mu sub j, we have to know something about the sampling distribution of mu hat sub j, this unbiased estimator of mu sub j. And one of the things that we need to know about it is its variance. So again, this is a random variable. It's a statistic computed from a sample. Because it's a statistic, a function of the sample, it's a random variable, and that random variable has a probability distribution. And one of the characteristics of that probability distribution is its variance. And so that's what we're talking about here. All right, so the variance of mu hat sub j can be shown to be 1 over r times the variance of the blocking effect plus sigma squared, which is the variance of the error term. All right, so that is the variance, that's the actual variance of mu hat sub j. And we can then take the square root of that to get an expression for the standard deviation of the sampling distribution of mu hat sub j, or in other words, the standard error of mu hat sub j. Okay, and so we have we have expressions at least for the variance and the standard deviation of mu hat sub j. Now notice that both the variance and the standard deviation of mu hat sub j, they involve both the block variance, sigma squared sub beta, and the error variance, sigma squared. All right, and the other point here is that we don't know sigma squared sub beta, we don't know sigma squared, and so we're not going to actually be able to calculate the actual values for the variance and the standard deviation of mu hat sub j. And so we're going to have to try to figure out how we can come up with estimates for the variance and the standard deviation of mu hat sub j. Okay, so that's an important point to consider. But also, again, remember that, and again, this is another important issue, that the variance of mu hat sub j involves both the block variance and the error variance. So the model variance components, sigma squared sub beta and sigma squared, are unknown. And because of that, as we were just saying, the variance and the standard deviation of mu hat sub j can't be computed exactly. We're not able to calculate, again, the variance or the standard deviation because we don't know these two variance components. Now, we can estimate them, and we can estimate them using quantities in the ANOVA table that we've been using and that we saw how to construct for the randomized complete block design. And so one way to estimate these parameters, these variance components, would be using method of moments. Okay, and the method of moments estimators for the model variance components are obtained from the mean squares for error and the mean square for blocks that are provided by the ANOVA table, and we utilize the expected mean squares of the mean square for blocks and the expected mean square for the for MSE, the mean squared error. We use those expected mean squares, and then we come up with these estimators for sigma squared and sigma squared sub beta. And so the estimator, and it's an unbiased estimator for sigma squared, the variance component of the error term, is sigma hat squared equal to the MSE. All right, so that shouldn't be too surprising. The estimator for the block variance component, sigma hat squared sub beta, is equal to the difference between the mean square for blocks and the mean square error divided by t, which is again is the number of treatments. So this is how we're going to estimate the variance components, at least in the context of this notes, and in doing calculations by hand. This is really the only feasible way of doing that. There are other methods for estimating the variance components. You can use maximum likelihood and so forth. But you really can't, in general, do that by hand because it typically takes iteration and so forth. And so we're going to use the method of moments estimators for the variance components. Now, plugging these estimators into the expressions for the variance and the standard deviation, and then simplifying the estimators of the variance and the standard deviation of the estimator of a treatment mean, so in other words, the estimates for the variance and standard deviation of mu hat sub j, are given by these formulas here. And so the estimated variance for mu hat sub j would be the mean square for blocks plus t minus 1 times the mean squared error divided by r times t. Now again, t is the number of treatments, so this is one less than the number of treatments. And we can also think of this as the number of degrees of freedom associated with treatments. The denominator is the total number of observations, r times t, the number of blocks times the number of treatments per block. And then once we have that, we can take its square root to get the estimated standard deviation of mu hat sub j. All right, and so that's given here. Now, a 1 minus alpha times 100% two-sided confidence interval estimate of the treatment mean mu sub j is going to be of this form, which should be familiar to us now. We're going to start off with a point estimator, mu hat sub j, and then we'll go a distance to the left and to the right, minus and plus, a distance that is called the margin of error. And the margin of error, again, is the product of an interval coefficient and the estimated standard deviation of the sampling distribution of the point estimator. Now, I've denoted the interval coefficient. All right, we see it looks like a t-value, but I've changed the notation just a little bit, and I'm putting an asterisk up here. All right, and the reason is, as we'll see, we don't quite know what that interval coefficient is equal to. All right, and so I'm really not going to say much more about that quite yet. We will in a few minutes, but the bottom line is that in order to construct this interval, we have to be able to calculate the margin of error associated with mu hat sub j. And that margin of error, again, is the product of the estimated standard error of mu hat sub j times the appropriate interval coefficient. All right, but before we can do that, we need a few more results in order to determine what that interval coefficient should be. And so we'll look at that in a little bit.